This is a short introduction to the HFCNN master's thesis project I produced. This project is constructed to be modular, built on the Hydra ML framework, and utilizes PyTorch Lightning. It has integrated multi-run support, which I'll demonstrate later, integrated TensorBoard and MLflow logging, data version control, built-in profiling, and support for learning rate schedulers, callbacks, and hyperparameter optimization. While built around PyTorch, the package is modular enough to work with any machine learning framework. Once the repository is cloned locally, we can begin using the application. The first step is to set up the conda environment. An environment file is provided for you. All we have to do is run conda environment create -f and then the name of the environment file, which is just in the root directory environment.yaml. In my case, the environment's already set up, so there's nothing further to do there. The next step is to install the package to our local Python distribution. We can use that using the setup file. We can do that with Python setup.py install. This install script isn't complete, but I have plans to finalize this before handing the software off to other people. To demonstrate how to use the code and some of the functionality, we're going to generate a simple action. We're going to produce a test set. In this case, we can look under configs and the default config here, and we can look at the action. The action here is default as train, but we're interested in not training, but producing a test set. So we can look in our action config folder, and we can see here we have a prepare test option. This is what we're interested in. We could go about changing the default action. This is possible. But instead of doing this, we want to do something a little more subtle. We're going to create an experiment. Here we're going to create an experiment called example.yaml. And inside the experiment, we can override the defaults. We're going to override the default sample with prepare test. We can also, if we want to, for example, increase the ratio of the dataset for the test split. We can look at our data module, our default data module, and we can see that the test split is set to 20% of the dataset. If we want to increase that for our purposes, in our example, we can specify the data module, and then we can do test split and set this to 30%. Now we have a simple experiment that's set up. How do we run it? The code is set up so we can just call it directly, and we can specify the experiment. So this is what we're interested in calling. As you can see here, it's applying two filters. By default, for example, we have our data selection, which calls two different filters, the missing data filter and the data selection filter. The missing data filter is just filtering out any unnecessary data that isn't found because something's missing. The data selection filter is actually going through and selecting data that meets the criteria of the heat load values. We'll let this run, and then we'll do some training as our next step. Now, to demonstrate a simple prototyping example, let's say we want to overfit our network. This will involve the train action, but not the default parameters we would normally use for training. Here, we've created an overfit experiment. We've changed the default action to train, and we will disabled the callbacks because we don't want an early stopping condition. Here, we're going to define the name experiment and change some of the parameters in the trainer and the data module to make the network more likely to overfit. Now all we have to do is run this command in our terminal. As you can see, we're quickly iterating through epochs, and our loss is slowly approaching machine accuracy. So the network is behaving as expected. On top of that, These runs are now stored in our output directory. We can specify the day, and we can see that I've run several overfit experiments, including this one, which is defined by the action name here. All of the relevant information about this run is being stored locally here, and you can access all of this information through MLflow and TensorBoard. For our final demonstration, we'll see how to use this framework to do easy multi-run hyperparameter optimization. We're going to start by creating a small experiment. We're going to define the sweeper to be AX, which is a Bayesian hyperparameter optimizer. And we're defining the parameters to be the optimizer's learning rate. We've defined the bounds and the distribution. All that's left is to run it. Here, we're going to be using the multi-run flag. This flag sets it so that every time there's a change in the parameter, a unique folder will be produced for that run. This will allow it to more easily be tracked by MLflow, so we can understand what the inputs are and what the metrics are of the network to see which hyperparameter optimization worked the best. A little bit of pre-validation, and then we'll get into training. We'll speed up this process and then see you on the other side. Now that our hyperparameter optimization is complete, I've loaded up MLflow. I pointed the backend towards the ML runs, which aggregates all the data from the various runs. Now all we have to do is pop this open in a browser, and we can see the relevant metrics and all the parameters for our network. This will allow us to better make decisions about optimizations in the future. That's it for this brief introduction to the framework. There's a lot more that it can handle and a lot more subtleties to running it, but this will give you a general sense of what it's capable of and basic idea of how to operate it. Thank you.